Today we're going to build an AVL tree. In order to do that, we're going to need a couple of documents that are in the module, and this is one of them. So we've seen that a binary search tree is usually better than a linked list in finding something. And when we say better, we mean has fewer comparisons until we find the object that we're looking for. You'll recall that a linked list is of order n, and a binary search tree is usually of order log n. I say usually because it can deteriorate into a linked list. It would be better if we had a data structure which was like a binary search tree, but better than it in that it had a minimum depth. And minimum depth means that it would be faster to find something, fewer comparisons to find something. And so our task is to find something that looks like a binary search tree, and we can find things just as we do in a binary search tree, but its shape is a lot better. And this is an AVL tree. So an AVL tree is height balanced. What do we mean by that? We look at every node and we look at the subtrees from that node. We take the height of the left subtree and subtract the height of the right subtree. And when we do that, we find a number that is either 1, 0, or -1. If it's either of those, then we say that that node is height balanced. If it's outside this range, it is not height balanced and needs to be rebalanced. We do this with a rotation. And there are 4 kinds of rotations, and they are listed here. And you have a PDF which diagrams those 4 rotations: single right, single left, double right, and double left. This is a lot to take in, so it's much easier if we do it with an example. So here we have an example. Don't worry about these things on the right here. These are nodes that I've created, and I can drag it just to make it a little faster. So we start out, we're trying to put these numbers into our tree. We start out with the 9 and we put that in as the root, and every time we insert, we have to calculate all our balance factors. This node has no subtree on the left and none on the right. It is a 0 minus 0. Its balance factor is 0, and that is fine. And now we put the 2 in. The 2 in a binary search tree goes to the left of our roots. So here is the 2, and now I have to recalculate my balance factors. 0 minus 0, this one is a 0, and this is 1 minus 0, so this is a 1. It's not the number of nodes. We'll see that more clearly in a minute. It's actually the number of lines. It's the length of the tree, not the number of nodes in the tree, that we are counting when we look at balance factors. Now we put the 3 in. That's 0 minus 0. 0 minus 1. 1, 2 minus 0. So this is a 2. Okay, this is a 2. This is not okay. We need to rebalance. So now I need to look at what kind of a rotation I need. So this is called the parent, and it's the parent not because it's the root, it's the parent because it's the one that's out of balance. So the parent is heavy on the left. That's because it's a positive number, and the left child is heavy on the right. I know that because that's a negative number. The parent is heavy on the left, the left child is heavy on the right. So I go to my description here: a parent heavy on its left and the left child heavy on the right. This is a double right rotation. Double right. I'm going to write this in here so that I remember. Double right. Okay, now go to this and look at how to do it. So I have a parent, a left child, and this NP here is a new parent. Let's just look at the nodes for a minute. Parent, left child, new parent. The new parent goes up. The left child is to the left of the new parent, and the old parent is to the right of the new parent. Okay, so this was the parent, this was the left child, and this one was the new parent. So we said the parent goes up, okay, so the parent, the new parent goes up, sorry, the new parent goes up, and then this was the left child and this was the old parent. And this is according to this diagram here. The new parent went up, the left child was the left child of the new parent, and the old parent was the right child of the new parent. And I have these triangles here, T1, T2, T3, and T4, which have to be reattached. Those triangles represent the subtrees. So T1 is the subtree rooted at the left child, at the left of the left child. So this was the left child. Its subtree rooted at the left was null. It had there's no T1. The T2 is the subtree rooted at the left of the new parent. That's also null. T3 is the subtree rooted at the right of the new parent, which is also null. T4 is the subtree rooted at the right of the parent, which is also null. So all of those T1 through T4 are null. They need to be reattached here, but they're null, so I'm done. And this is my new AVL tree, and if I put my balance factors in, that's a 0, that's a 0, and in fact that's a 0. So I've got a beautiful tree right now. And now I am ready to put in my 6. And now if I do balance factors, 0, this is a 1 minus 0, so this is a 1. This remains a 0. This is a 1 minus 2. So this is a minus 1. And everything is fine. The next thing that I have to put in is a 5. So my 5 goes in. Redo my balance factors. This is a 0. This is a 1 minus 0. This is a 2 minus 0. And I can see here that this one is not okay. I could go further. I have no need to, but I'll show you why. This is still 0. This one is a 1 minus 1, 2, 3. So this is a negative 2, which is also out of balance. This 5 was the last one I put in. Going up from there, the 9 is the first one that's not okay, and that is now the parent. I will fix this, and in fixing this, this balance factor also gets fixed. In other words, you don't do them all, but you start from the node you just put in, you go up your tree until you find one, the first one that is out of balance, and then you fix that one. So here I have a parent who's heavy on the left and whose left child is also heavy on the left. Let's look at what that says. A single right is the parent and its left child are both heavy on the left. So I need to do a single right rotation. I need a single right. Let's look at here, a single right. I identify a parent and a left child. The left child goes up, the parent comes down. So I've drawn it again here. The left child goes up, the parent comes down. The 2 and 3 stay where they were before. It's just from the parent that gets altered. Now I look at these balance factors again. This is 0 minus 0. This is a 0. This is a 0. Leaves are always zeros. Okay, this is a 1 minus 1. So this is now a 0. And this is a 1 minus 2. This is a negative 1. So here we have our AVL tree, all perfectly balanced. The next number to go in is a 12. And the 12 is going to go in right here. I put the balance factors on here, and we can see now that it is the root that has a problem. This now becomes the parent node, and we can see that the parent is heavy on the right and its right child is also heavy on the right. If we go to our document here, that's going to be a single rotation. When the parent and the right child are heavy on the right, it is a single left rotation. So this means we do a single left and look at our diagram for that. Single left, we have a parent and a right child. The right child goes up, the parent comes down. So looking back at this diagram, the right child is the 6. The right child goes up, the parent comes down. So the 6 is now the root, and the right child, its left child, is the old root. This in the diagram, this was the right child. So the right child went up, the parent came down. And we have to see what's attached. So T1 is the tree that's attached to the left of the parent, which is the 2. And that remains attached to the left of the parent. So the 2 stays here. The T2 was the left subtree of the right child. Here is the right child. Its left subtree was the number 5. Let's see what happened to T2. It is now the right subtree of the parent, and the parent was the one with number 3 in it. So T2 was this subtree here, the left of the right child, and it got attached to the right of the parent here. T3 gets attached to the right of the right child. Right child is the 6, so T3 is going to go in here. We just have to see what T3 is. T3 was the right of the right child. So whatever is here now goes in here. And we can see the result here. And you can see that it's continually rebalancing. It got a little bit out of whack here, and it came to a better shape here. And the next thing to go in is the number 10, which is going to go in to the left of the 12. I put in the number 10 and I did the balance factors. it's only really necessary to do the balance factors up the tree to the root from the node that you just put in. So it really wasn't necessary for me to do these on the left. So from the 10, its balance factor is a 0, it's a leaf. The 12 has a balance factor 1 minus 0, so a 1, and the 9 is a 0 minus 2, so that's a negative 2, which makes it out of balance. So I look at this is then the parent. The parent is heavy on the right and its right child is heavy on the left. That tells me it's a double rotation. So the parent is heavy on the right and the right is heavy on the left. It's a double left rotation, double left. Okay, I need to identify a parent, a right child, and a new parent. Parent, right child, and a new parent. And while I'm here, I can also identify that T1 is null. That T2, T3 are null, and in fact, T4 are all null. I just wrote that all in for you here. So all of those T's are null, and we have to see what happens. Let's see if I can. The new parent goes up, the old parent is to the left, and the right child is to the right. So the new parent goes up, and I rewrote it here for you. The root and the left of the root remain the same. Anything that changes is just from this parent onwards. The new parent went up, the old parent went to the left, and the right child went to the right of it. And if you put balance factors on all of these, they're all 0. And you can see, in fact, that is a complete, no, that is not only a complete, that is a full tree. It's about the best that you can get. And it is beautifully height balanced. If we compare this with the binary search tree that we would have produced with the same input, let's look at that. You can see it turn on the right, and you can see that to find a number 5 takes 1, 2, 3, 4, 5 comparisons, whereas here it takes 2. Maximum is 2 in this tree, and here we have some that take 5. And so we can see that this, even just for a few numbers, a number of searches is much better with an AVL tree than with a binary search tree.